All right, today we're going to talk about generalizing two formulas that you're familiar with about determinants. So the first one that we have is this one about inverses. And you may notice that, in fact, this right here in the bottom is a determinant. So we can write this instead, we can write it as 1 over the determinant of A times some matrix that seems related to the original one. So this other matrix is related to A. We're not sure exactly how yet, but we'll get there. And what we want to be able to do is to find a formula like this for any size matrix, not just a 2 by 2. The formula may be slightly complicated, but at least calculating it will become intuitive, and it'll be more clear why this determinant is here, and more importantly, why things get moved around in the matrix. But first, we're going to focus on generalizing a different formula, and that is the one for a 3 by 3 matrix for the determinant. So if we take a 3 by 3 in the determinant, right, we have 6 terms in this, but you can write this in terms of other determinants. You can write it as A times the determinant of the matrix E, F, H, and I minus B times the determinant of D, F, G, and I plus C times the determinant of D, E, G, and H. So you have this idea that you can construct and compute bigger determinants using smaller ones. So the main idea here is this is a smaller determinant. Right, so what we want to do today is generalize these formulas and give you the power in order to calculate both inverses and determinants. So the main tool we're going to need, which isn't actually quite obvious, but we need this concept of which submatrix. So right here, we're looking at a certain submatrix inside our bigger one. And it turns out the inverse, it's happening in there too, albeit it's not quite as clear. We need to figure out what that's called and how that works. So before we generalize that, we're going to talk about minors. So a minor is just a matrix, a submatrix. So it's just a submatrix, so it means smaller than before. And specifically, we have that, we're going to denote it as this. So this is just an example. 1, 3, this just means that we're going to delete the first row, and this 3 means we're going to delete the third column. And that's going to be a minor. So let's just do an example. What does this look like? So for example, if we have the matrix, these matrices are going to be big today because we want to generalize these formulas. So if you have this matrix, the 1, 3 means we're going to delete out the first row, and we're going to delete off the third column. And so this particular minor is going to be just these entries right here. So this right here would be a submatrix that corresponds to the 1, 3 minor. And what we're going to do is we're going to write both the determinant and the inverses in terms of these minors. So whenever we write this notation here, this right here is just a submatrix. That means to delete certain rows and columns. All right, so we can probably go back up to here and guess kind of what's going to happen is that we are going to, the formula is going to say something like, we're going to have to go through A, B, and C. So we're going to go through one column and we're going to add up different products of minors with A, B, and C. So for example, there's another one. And finally, this last submatrix is hidden right in here. So that's kind of where the pattern is going. So in general, what does this look like? We have the determinant of A is going to be equal to the sum of certain entries times the determinant of a minor. And it alternates. All right, so just to recap, this means we're going to sum. It's going to alternate over a product including the determinants of minors. All right, so this is the product and the determinant of the minors right here. All right, so that's the general formula. This may seem overwhelming. This is just a sum of a product. So just like dot products, when you matrix multiply, it become very intuitive. This formula is just multiplying pairs of things together and then adding or subtracting up all the results. So let's just go ahead and dive into an example. And we're in fact going to use the same one I did before. So we're going to use this matrix and we're going to calculate the determinant of this matrix. Oh no, it's a different matrix. Let's calculate the determinant of a different matrix. One that's easier to do. And what we're going to do is we're going to sum over a row. So the row we're going to sum over is this first row right here. So what we need to do is for every one of those entries in that row, we need to find the corresponding minor. Now, what may seem weird is the minor is going to be everything that's not in that, everything, you're deleting that row and column. So if we're going to expand over that row, what we're going to need to do is we're going to need 4 different terms. So what are those terms? Those terms are going to correspond to, you're going to have one entry of that row times the determinant of the corresponding minor. And then we're also going to do the next one. And we're going to keep going. So for example, now we have the next one is go to the next one, which is the 0 right here. And the corresponding minor is just going to be that one. And finally, we have And so basically what this says is we can boil down calculating the determinant of a 4x4 to instead calculating 4 3x3s. All right, and that may seem overwhelming. There's a lot of work here right on the screen. But on the other hand, I want to point out the advantage of this is that there's some zeros here. So these last two are going to contribute nothing. In fact, we don't have to, if we didn't want to, calculate the determinant of these later two because they're just going to get zeroed out anyways. So in some sense, we've halved the amount of work that we have to do. So now it's just a matter of calculating the determinant of these guys. The determinant of our original matrix A is going to be a sum of products. So the first term is going to be 3. So that 3 comes from up here times whatever the determinant of this matrix is. This is just the determinant of this guy. So the determinant of that one is going to be, that gives us a 4 and 6 minus 12. So that turns out to be 22. So that's 22. All right, and then we're going to do it over here too. We're going to take this 1. Now we're going to calculate the determinant over here. So here we have, that's a minus 4 right there. And similarly, a 6. Except we also have that one right there. So altogether, that's going to give us minus 12. So this is just the determinant of that matrix right there. All right, and then we're also going to have 0. For the sake of brevity, I'll just tell you that this determinant turns out to be 17. Again, we don't actually have to compute it because it will get zeroed out when we multiply it by 0. And similarly, we have a 0 here. And that one turns out to be multiplied by minus 4. All right, so we're going to add these up, except there's one minor wrinkle in that we have this alternating sum. We're going to alternate them. And how it alternates depends upon what the I and the J are, which row you pick. So here we pick the first row. So what's going to happen is we're going to start with a plus because this I is equal to 1. And maybe a better way to visualize this is this corresponds to a little checkerboard pattern. So this term right here corresponds to this checkerboard pattern and kind of gives you an idea of which term is plus and which term is minus. So here this says we're going to use this plus minus plus pattern. So what we're going to do is down here we're going to use a plus, a minus, a plus, and a minus, right? So keep in mind the order which we do these matters. This was the first, second, third, and fourth term going from left to right, and then, yes, top left, top right, bottom left, bottom right. 1, 2, 3, 4. So that's a minus, plus, minus, plus, minus. And when we add these together, we're going to get 78. So this may seem like a lot of work, but again, we can leverage a lot of the work away if we recognize if there's a column of zeros. You get to pick the column, sorry, you get to pick the row that you want. So you get to pick whichever row you want. And it turns out that this works with any column as well. It's the same idea, the same formula, almost exactly. The only difference is you're going to switch this AI to an AJ. It's pretty much the only thing that's going to be different. And you can apply the same idea. You go across the row or column and add up the product between the minors and the corresponding entries, add them up, and you get the determinant. All right, so that's an example of how. All right, so one really cool thing about the determinant is that you can use it to calculate the inverses of any general matrix. So in particular, we're going to generalize the formula that the 2 by 2 inverse is equal to 1 over AD minus BC. That's a determinant times the matrix that's airily similar to what we started with. Right? And it turns out this is actually coming from determinants as well. So the general formula says that we're going to take the ij entry of the inverse is equal to plus or minus, based upon exactly where you are in the matrix, times some ratio of determinants. So this just says that the ij entry of the inverse is plus or minus, based on that checkerboard pattern we did before, of a ratio of determinants. And one of those determinants is a minor. So we have to calculate the determinant of a bunch of minors, but if we do that, we can automatically just write down what the inverse is. All right, so one word of warning here is that this is in fact reversed. So that's going to come up in just a second when we go through an example. All right, so let's go ahead and see this formula in action. Before we do that, I want to point out that, in fact, this right here, this is the determinant. So in the 2 by 2 case, you're actually dividing by every term. You're dividing by the determinant. And here again, you're also dividing. In this new formula, you're also dividing every term by the determinant. So this is a nice generalization of this 2 by 2 formula. All right, so let's put this in action. Let's put this in action. We have 2, 1, 0, 0, 1, 1, 0, 1, 0. Okay, so there are a lot of zeros in there. So this formula is really nice when there's enough zeros that some of the determinants that you have to calculate will be 0. Otherwise, you actually might have to do a lot of determinants. But this one shouldn't be so bad. So to use this formula, we need two things. We need the determinant of A. So the determinant of A in this case is going to be, well, we have 3 positive terms. Turns out those are all 0. So those three diagonals give us that there's 0. And then the 3 negative terms, one of them is actually going to end up being not 0. So the negative terms, that one's 0, that one's also 0, but this last one turns out to be 2, so negative 2. So the determinant of A is 2. So what's going to happen is we're going to, according to the formula, we're going to divide every entry by negative 2. And now all we have to do is to compute all of the minors, all the 2 by 2 minors and their determinants, and it will just give us the inverse right away. But we have to place them correctly, and we need to keep in mind there's this plus or minus as well. All right, so what we're going to do is we're going to do a few example entries. This can be somewhat tedious, but it shouldn't be that bad once you get the hang of it, and once you can spot how to calculate the 2 by 2s. So we're just going to do a couple of the entries and just fill them in to give you the answer at the end. All right, so let's do the first entry. We want to calculate in this inverse. We're going to calculate the inverse, and we're going to calculate the very first entry of this one. So this is the 1, 1 entry. And to calculate the 1, 1 entry, we need to calculate, according to the formula, we need to calculate the 1, 1 principal subminor. So we calculate the determinant of that guy. That's going to give us a minus 1. Right? Because there's a minus 1 here on the diagonal, on the negative diagonal, and 0 otherwise. And we're going to divide by the overall determinant, which is minus 2. So we're going to divide by this overall determinant. And so that's going to give us the first entry, except we also need to keep in mind whether it's plus or minus. So this here just means we're going to have a checkerboard pattern of pluses and minuses. So much like before, we're actually going to get a plus. So that's the very first entry. All right, let's go to the next one. So now we're going to compute the next entry. And we're going to do something very similar here. So this one right here, this is the 1, 2 entry. Keep in mind, when we say 1, 2, that means the first row and the second column. But now when we compute the determinant, this is reversed. So what that means is we're going to compute the determinant not of the 1, 2 minor, but of the 2, 1 minor. We're going to temporarily delete the 2, 1 entry and its row and its column. We're going to delete those guys. So the only thing that's left here is we're going to do this. We deleted the 2, 1 entry and compute the determinant there. And the determinant there is 0. Right? That's because they're all, those two rows are multiples of each other of what's boxed in purple. So we know the determinant is going to be 0. You can also use the formula too. But because they're multiples of each other, we know that the determinant is going to be 0. And we're going to divide that by minus 2. And just for emphasis, we would ordinarily need to figure out whether we plus or minus. So since the first one was a plus and we need a checkerboard and the second one's going to be a minus. All right, let's do one more. Just so you get the hang of it. So let's go ahead and do this one right here. So this one is the 2, 3 entry. So what we're going to need to do is calculate the right minor in the matrix. Right, so that's the 2, 3 entry. So we're going to need to calculate the 3, 2 minor. We need the 3 and 2. So we're going to delete this entry. This is the 3, 2 entry right here. That's the 3, 2 minor. So we're going to delete that row and column temporarily and just look at what's left and calculate the determinant there. The determinant there is just 2. 2 times 1 minus 0 times 0 for that determinant. So that gives us a 2 for the determinant. And we're going to divide that one by minus 2. And then the alternating pattern, since we need a checkerboard pattern, this was a minus, this one would be a plus, and this one would be a minus. All right, so we got 3 of the entries, and you can continue this for all of them. It turns out a lot of them end up being 0. So just for completeness, let's just write down what we get as a final answer here. So the final answer, you would get 1 over minus 2. You get 0 over minus 2. Here you get 0 over minus 2. 0 over minus 2. Minus 2 over minus 2, or plus 2 over minus 2. And 2 over minus 2. And you get this pattern. And of course, you can simplify this if you want, but this just becomes the matrix 1/2, 0, minus 1/2, 0, 0, 1, 0, 1, minus 1. So this would be A inverse. So this is a nice way of calculating the inverse without necessarily row reducing.